In this video, I'll walk you through getting started with Foldit, the program we'll be using to design mutations in the beta-glucosidase B protein. This isn't meant to be a comprehensive guide to Foldit. If you want to learn all the ins and outs of how to use the program, I'd encourage you to visit Foldit online and complete the tutorial they've set up. It will take you through puzzles of increasing complexity that introduce you to all of the Foldit tools and show you how to use them to solve challenging protein structural problems. Instead, in this video, I'll show you how to launch the standalone version of Foldit that we'll be using for our experiment focusing on BGLB, how to load the data files needed to view and manipulate the protein structure, and how to make and evaluate mutations. Before we get started in Foldit, make sure you have downloaded the 5 data files needed to model BGLB in Foldit. The link to these is in the lab handout. Save the files to your computer somewhere you'll be able to find them again easily. The first thing to do is open Foldit by clicking on the program icon on the desktop or in the Start menu. You should see something like this that shows some of the academic institutions involved in creating Foldit. To launch it, click the green Play button at the bottom. Give it a minute and you'll see 2 options pop up: Import PDB FASTA or Load Session. We want to select the first option to upload the data files we need to work on BGLB, so click that button. Navigate to the folder where you saved the 5 BGLB data files and select all 5 of them at the same time. Now click Open. Wait while the program opens the files. This might take a minute. Once it's done, you should see your BGLB protein structure appear, looking something like this. Now, before we get into working with the structure, we're going to change a couple of the options for how we are viewing the protein to make it easier to see features we want. Click on the green Foldit Home button on the bottom left, then select View Options. Under the Color menu, make sure that Score/Hydro plus CPK is selected. And under the View Protein menu, select Cartoon Thin. Then click the X to exit the View Options window. Now this looks like a tangled mess of nonsense. What exactly are we looking at here? We're looking at the fully folded structure of the beta-glucosidase B protein. Notice up here at the top of the window we can see the energy score. In general, proteins fold to reach their lowest energy state and greatest stability. This energy score is calculated by the underlying Rosetta algorithm based on the sum of all of the interactions and bonds formed all along the protein. As we make changes to the protein, we'll want to pay attention to this score. The more negative it is, the more stable the protein structure. Going less negative means the protein is less stable. This cylindrical tube-like part of the structure is the polypeptide backbone. And the different colors along the backbone, from green to a kind of peach to faint red, are reflecting the energy score or relative stability of that bit of the polypeptide, where green is more stable. These squiggly bits projecting from the backbone are the unique side chains or R groups of each amino acid. The colors you see are due to the color view option we just selected when we started, with hydrophobic side chains color-coded orange and hydrophilic side chains color-coded blue. This structural view uses the same sort of condensed organic chemistry line angle drawings that you've been introduced to previously in the class, or if you've already had organic chemistry, you're already very familiar with. Just as a reminder, in those condensed views, carbon atoms aren't shown, but they are implied at every corner and end of line. And hydrogen atoms aren't shown at all. We just know they have to be there to satisfy carbon's valence. In the Foldit structure, we see that same condensed line angle representation of the side chains. Since we selected CPK in the view options, important bonding atoms of the side chains are color-coded for us, with nitrogen colored blue, oxygen colored red, and sulfur atoms colored yellow. The carbon atoms of the side chains are not colored in, and none of the atoms are color-coded in the backbone, only in the side chains. Just as with our condensed structural drawings, Hydrogen atoms aren't shown, we just know that they're there. So for example, if we focus on this particular amino acid down over here near the bottom of the structure, in the amino acid side chain, we see 4 corners or angles and then blue. So we know that side chain has 4 carbon atoms and a nitrogen or amino group at the end. If we look up our condensed amino acid structures, we can see that that's lysine. Now we're not going to have to try to figure out what each of these amino acids is in the structure. Foldit makes it easy. We can just click on one, hit the Tab key, and a pop-up will appear telling us what amino acid it is and where it is in the primary structure of the protein. So this is lysine, and it is amino acid number 437, counting from the N-terminus or beginning of the protein. Okay, now we're ready to start playing with the structure. Since this is a 3-dimensional structure, you can turn the entire protein to view other sides. To do so, click on the black background and drag in the direction you want to turn. It's important that you click on the black background and not on the protein structure itself, because you could inadvertently make changes to the structure. If you think you might have accidentally done so, you can click Ctrl-Z or Command-Z to undo, or you can use the handy Undo menu to reset the puzzle to its starting state by clicking U, then selecting Reset Puzzle. In this view, we can just barely make out the substrate molecule or ligand in the active site of the enzyme. It's this brownish structure here in the center. To get a better look at the interaction between the ligand and the enzyme, we can turn the structure by clicking the black background and dragging, and zoom in using the touchpad, touchscreen, or mouse wheel. Now we've got a much better view of the active site of the enzyme and the amino acids that are close to or interacting with the ligand binding there. Let's take a closer look at this amino acid here. By clicking on it and then hitting the Tab key, I get the information window that tells me that this is amino acid number 409 in the polypeptide chain, and it's a tryptophan. Now I know that this sugar ligand is polar, and I know that tryptophan is nonpolar and aromatic with these big carbon rings. So maybe I don't think this tryptophan is interacting very much with the sugar. That's in contrast to some of these other amino acids in the active site that are actually forming hydrogen bonds with the ligand, as indicated by these wavy blue and white lines. And if you click on it, a pop-up window will tell you exactly which amino acid that is and whether it's a hydrogen bond donor or acceptor. I wonder what would happen if I change this tryptophan 409 to another amino acid that is more polar. Would the interaction change? Would it now bond with the sugar? Would it alter other nearby interactions and structures? Well, let's test it out and see. If I click on tryptophan 409 and hit the M key, it pulls up a menu of other amino acids I could mutate this residue to. I'm going to change it to tyrosine, which also has a ring structure in it, but has a hydroxyl group as well, making it more polar than tryptophan. So I click on the tyrosine and presto, tryptophan 409 is now tyrosine 409. Now take a look at the energy score. It's dropped by about 0.3 from where we started, so become less negative, meaning the protein is slightly less stable. We could hypothesize potential explanations for this. Maybe the tryptophan was interacting with other nearby hydrophobic side chains and we've now lost that. Who knows? But now what I want to do is have the Foldit program nudge nearby amino acid side chains into different positions to see if there's a more stable structure to be found with this mutation in the polypeptide. I'll use the wiggle and shake tools to do this. And more specifically, I'll be asking the program to just move side chains, not the backbone. I don't want the program to analyze all of the amino acid side chains, only those nearby. So I'm going to use the Select tool to select 30 of the closest side chains to the mutation. In other words, the mutation's nearest neighbors. First, I need to click on the mutated amino acid, the tyrosine I swapped in for the tryptophan. Then on the keyboard, press Control, Command on a Mac, and Shift. Then I drag the cursor. You can see the number of selected segments change in the selection interface window at the top left as you drag. I'll stop when I get to 30 or thereabouts. Looking at the structure, I can see the selection highlighted in pink. Now I'll use the wiggle and shake tools to nudge these side chains and see what happens to the energy score of the protein. The wiggle side chains command is the E key. When I hit it, the region I selected starts blinking as the program does its thing. And I can also see that I've now got a counter in the selection interface window that shows the elapsed time and also the number of wiggle cycles the program has gone through. After about 10 cycles, I'm going to stop the wiggle by hitting stop. My energy score didn't change much. Now I'm going to use shake, which gives a bit more of a nudge to the region, by hitting the S key. After a few cycles, I can see nothing's really happening with my energy score, so I'm going to hit stop. Then, just for good measure, I'll give the region another wiggle and see what happens. Not much. Changing this amino acid from tryptophan to tyrosine doesn't really seem to impact the energy score very much. So this residue might not be terribly important for the structure of the protein. We'd obviously have to do some more testing to be more confident of that, but it's a hypothesis you could make. So there you have it. This has been a quick introduction to how to view our protein of interest in Foldit, how to select and mutate specific amino acids in the polypeptide, and how to model the structural impact of that change using the wiggle and shake side chains tool. Now before I close the program, I'm going to reset the puzzle so I don't accidentally leave that mutant tyrosine there at position 409.